Okay, hi. How was the practice? Did you succeed creating a makefile? Yeah. I created my version right now, and I uploaded it to as a new commit to the repository. So if you pull in every branch, you have a version for GNU and for Intel in the corresponding branches. If you have changes, maybe you should commit previously your changes in the branch. Anyway, in my case, we just pull. I get okay. I get this new commit here. That basically I didn't overwrite the main file. I created a new one just to avoid any confusion. So this, for example, is for ICC. As you can see here, I basically translated the slide with this to this example. So that way, let me check. In this machine, going to use finish try for this. Okay. Okay, yeah. So GNU so, for example, using Intel compiler, I need to load Intel stuff, the Intel math library, and with this, well, I didn't tell you, but when you execute make, by default, it executes the make file with that name. The first letter, the name make file can be capitalized or not. So the first letter can be or not, like this. And but you can also select the specific make file you want to use with -f. So with -f, you can select a different file as make file. So here I'm using this one. Let me max this to have a couple of okay, I'm already here. So make file alt is like this. So no. So it's just applying the implicit rules. I don't have the explicit recipe here. I have this dependency established here, and I can choose. I can choose between release or debug, like this. So as you can see, different flags are applied. And you have this example. So if you want to improve your make files, for example, for the tasks, you could use this as a recipe or your own. Do you have similar solutions? Any of you? Did you get a make file, a working make file at home or in remote? Any doubt, any question? So you can check my solution. Just pulling it's in the repository. Sorry, here. So you can check here. I have a new commit in both branches. You can check that in the GitLab interface. So 5 commits. This commit is this new make file with this debug release stuff. So in both branches, you have a similar new make file. Of course, you could join both make files in just one make file, choosing the compiler and the parameters depending on if you are using ICC or GCC. I didn't put information in the slides about conditions, but you can also have some commands, maybe like pragmas, similar to that, in makefile to establish conditions. So you can fix some conditions and perform different actions depending on the conditions. But I usually don't use. I don't usually use conditions in my makefiles. Any doubt? Any question? Otherwise, we're moving on. Okay, let's go ahead with CMakes. So the main problem with makefiles is that the makefile usually is rigid, and it's not easy to customize the makefiles for different platforms. So that's the origin of CMake. So the idea of CMake is a cross-platform, a compiler agnostic. It can be used with other systems, even though it's quite common to combine CMake and Make. CMake can be used with other building stuff, like Ninja, for example. So it's used to be, it's designed to be used on top of other build environments like Make. It's cross-platform, so it can be used in Windows, Mac, or Linux. Supports in-place or out-of-place builds. I don't know if you're familiar with this. So far, in these examples, we're using in-place compilation. In big projects or even in medium projects, this is not very. This is not a good idea, because you are mixing, you are putting together binaries, source files, headers. So usually in a real project, you have directory hierarchy, and you usually don't want your binaries, the result of the compilation and the linking, mixed with your project stuff. You want this in a different directory. That way you can get rid of all the result from a compilation, just removing a directory, for example. So this is what out of place or out of source or shadow building, in these three names are the same. That means you are compiling your sources in a different place. Shadow building is also a common way to call this. This is very typical when you are using CMake. With CMake is quite the orientation of CMake usually is to execute this out of source building. Basically, it means something like this. This well, maybe it has no sense, but imagine when you are compiling when you are building a project out of source, usually you create a directory like this, build, and you want your all your stuff from the result of the compilation and the binaries and so on in this subdirectory. That way, the rest of your project is not modified by the compilation. No additional files are created everywhere. So that's something you want. So we'll see how to do this with CMake. With CMake is very easy, but with Make you can also do that. You can. My make file is not written to allow this, because now it's not finding the sources. CMake create a make file that can do this. So we'll see how to do this with CMake. That is quite comfortable. So this is basically these are basically the most important aspects of CMake. You can also have different builds. That means, for example, release, debug, but it's very easy to create different builds for the same source tree. You can also add libraries, dynamic and static linking. Well, what you could expect of this kind of software. So this is CMake is the modern way of doing something. Classically, was performed with AutoTools. AutoTools was a project like CMake and GCC by GNU, but nowadays AutoTools are totally out of date regarding CMake, because CMake is really easy. The learning curve is actually with AutoTools is quite steep, and with CMake is quite easy to start. Basically, in CMake we need to write a file like this with this name, CMake list. It's a file that is very easy to understand. It's easy to write, and well, we'll see now an example. The drawbacks of CMake, well, the learning curve is good, but not so easy as Make. It depends, but it's complex to really know every option in CMake, because it's huge. So you can learn some basics, and with that probably you have enough. In my case, I just know the basics, and I'm able to write my CMakes and to exploit other CMakes, but I'm not able to do complex stuff with CMake. I need to check the documentation if I need to do something out of my usual use of CMake. So this is an example of CMake list. There's 3 lines. Usually you put a name to your project. You establish the version of CMake you require. This old version, but well, usually it's enough. If you need recent features, you should put a recent version, but that way people with the old machines maybe cannot build your project. So in the end, here usually you can see an old version of CMake like this one. And finally here, I'm just telling what's the name of the binary I want to build, and the source files my binary is depending on. In the end, CMake will create a make file to compile these files, these source files, and create my target. That's basically the idea. So the typical workflow with CMake, I don't know if I have some CMake here. I forgot to look for one. Let me check. Yeah, but this is not not my project. Well, we could use the CMake for other project. Okay, yeah, this can work. Okay. So here I have a project. I can get rid of this. So I have some C files, and I have a CMake list. Don't worry about the content right now. The important thing about CMake is just the usual workflow is like this. I create the directory where I want to put all the stuff from the compilation. Usually the name can be build. This is the name I usually choose. And I perform something like this. Sorry. You need a specific module in Finisterrae. With something like this, I'm telling CMake I'm in the directory where I want to create the stuff, and here now I have all this stuff, including a make file CMake has just created, and out of this, in my original directory, nothing was changed, nothing was modified. So now in build, I can execute make, and all this stuff from the compilation is in this subdirectory. That's good in great projects because here outside everything was like originally, and here I get all the results of my compilation in this folder, in this subdirectory. Here, well, here I have some examples of a matrix multiplication. Here are a lot of stuff that is generated internally by CMake, the object files. Okay, so this is basically how this works. So you create your CMake list.txt like this in your project. You create a build subdirectory. You change the directory to the build CMake ... That means you're basically here you are telling CMake that your CMake list, that is the main file, telling CMake what you need to do, what it needs to do to build your project. So that is in the parent directory. And after this, CMake is generating the real make file you will use to generate your project. So after this, you just write make, and you're using the make generated by CMake. As I said, you could use Ninja or other development tools to finally create your project. So CMake, instead of make, could generate a Ninja if you prefer this tool. So this is quite easy in the end. So now I'll show you some alternatives to create more or less useful CMake project with a good hierarchy of directories. And after that, I'll give you another task related to CMake to create your own CMake to try to play with this. So in this case, in this very simple example, we're working with a project hierarchy like this. So we have the root directory of my project. In this directory, I have all the source files without any specific order. This CMake list files, that is the CMake file to build the project, and I've created this directory to put all the stuff for the compilation here. So this is my current scenario. That is not especially good when the project is medium, large size. So some basic stuff about CMake. You can also, of course, tell CMake what flags you want for the compiler. So you can indicate with this variable CMake C flags the flags that we'll use in the make file to eventually create your project. So you have a condition for C, another one for C++. So you can have different flags when you're compiling with C and C++. These are the equivalents to C flags and CXX flags in make files. And in the end, this will create the corresponding make files with this information. You can also tell CMake which libraries you need to link your project against. So you say, for this target, I want to link this library. There are two different notation for this. You use these target link libraries. You write the target, the binary, the final binary, and here you can indicate like this, or just with this part. Well, again, this basically means this. Means you have something like this in a path. In this case, CMake can find this file. This is a static library, but you could also use a dynamic library, a shared object. So you can also add messages. So output a text that you want CMake to get a more verbose compilation. So message, whatever, with the name of variables if you want to see the value you're using in your variables. Like in makes, you can use this. Well, in our previous examples of make, I use this notation with parentheses, for example, for the build variable. But actually in make, you can also use the curly braces, like in bash. So this is also okay. So here, instead of the parentheses, we're using the curly braces. Both are okay. Both are okay in both CMake and make. Okay, so we have also some facilities to for example, well, we can use variables. So this at executable was already here in the original CMake here, but instead of write everything here, we could use a variable. So here previously we can set some variables, some values, set that variable, sorry, with these values. And after that, we can use this variable in multiple parts of our CMake file. We can also have conditionals. So depending on the value of one variable, we can or not, in this case, include some directories. This is the in function that allows CMake to find the different packages in our system and create a make file according to this. So different packages have different ways of working. When you are using, for example, in this case, the CUDA toolkit, that is the CUDA, the something NVIDIA is providing, you should read the documentation for this CUDA toolkit to know which variables this package is creating. That way you can use these variables to compile your project. So in this case, CUDA toolkit is providing this variable. So if CMake is able to find the package, the package is also providing these directories, these paths with the headers we should include in our program to compile against CUDA. So in this case, if CMake is able to find this package, we are telling here that the directories included or the value of these variables, the value of this variable that is these headers should be used as include in when we are compiling the sources. There are different variables that are built in CMake. CMake sort like this. So these are built-in variables, and other ones are these ones. CMake source dir, CMake binary dir, project source dir. So we can indicate different paths with these variables. Just using set, we can assign the value we want to the different variables. And well, this is the typical minimal organization we could apply in a project. So instead of the naive approach with everything put together here in just one directory, and we just create the build directory to compile there, we can also organize everything a little bit. So usually we have as a source directory with our source files, and a CMake file, and we have our headers. They include the files we include in C or C++ in a different directory, and of course our build directory. So this is a better organization, and for this we just need to provide in the source directory a CMake like this. This is another example. Again, we have the final binary we want, the different sources we have here in this directory. In this case, we want to link against a library, imagine the mathematical library, and we're telling CMake where our headers are. Our headers are here. Dot dot. I know. I assume you know this. What dot dot means? Means the parent directory. So regarding a source, the parent directory, and then inc subdirectory. So we are telling CMake that here the headers can be found. So after this, we also select, in this case, the C flags, the flags we want to apply for the compilation. For example, WAll, WExtra, March native, and OFast to get the best possible performance. So this is just an example. So this is a minimal CMake with a better organization than the previous example. Imagine, in addition to create an executable, we also want to create a library. So we want to generate two different binaries. One executable and one library. Well, it's very easy also with CMake. Again, we put here the executable we want with the corresponding dependencies, and here we also create a library with an analogous command. So add executable, add library, the same syntax, the name of the binary we want, and the dependencies. In this case, my X again will be linked against the mathematical library. I will also link against the library, this library and building. So this is the library we're building in the same project. So in this project, in this CMake project, we are creating a library, mylib. This library is created from these source files, and this library will be used in the same project to create my X, that is the binary, created with this other CMake command. Now, well, finally, like previously, where to find the headers. So the header files, you know, the header files are the files .h and other extensions, depending on C++. In C++, sometimes you find HPP. Well, it depends. There are different extensions, but they are usually in a subdirectory named include or a similar. Well, in this case, the name is just inc. And again, the flags for the compilation. So we are just, from this slide to this slide, we are just adding the possibility to create a library and link our project against that library. Okay, a good idea, usually it's a good idea to just put the library and the executables we are generating in a project, in the same project, in different directories. That's a good idea. So we can also do that with these three variables, CMake libraries, CMake variables. So this variable is for the executable. This other one for the dynamic libraries, and this one for the static libraries. In this case, I'm using the same path. These paths are regarding this variable, and this variable, if you remember, I don't know what was this. Here, These are the variables regarding project organization. So with these variables, checking these variables, we can know where our project is, so we can create paths relative to these directories. So using these new variables, we can improve our organization like this. Sorry, oops.
Sorry, Emilio. One question. Does the order matters? Because you link the library before define the library. If you can put the sample of the previous.
Yeah, I know what you mean. Yeah, the order actually here.
No, it's not this one.
Yeah, I know. Here.
Mm-hmm.
Yeah, actually, it's not relevant because this kind of files is like a static definition. So these files are interpreted before CMake doing anything. So are parsed. Sorry. So the order is not relevant in general. So you can just put your stuff here in whichever order, and it should work the same.
Okay, perfect. Thank you.
So usually you here organize the stuff in a way that is that you are comfortable with. So to read, to improve the reading of the file. But yeah, that's a good question. That was the question you were. Okay, yeah, you were writing.
Yeah, it's in the chat. Yes.
Yeah, sorry, I'm not checking the chat usually, so just that's a good idea. It's a good idea that you just open your mic and ask me the question. Okay, so we're improving our project hierarchy using these three variables. So as I said, it's a good idea to have your executables in one directory, your libraries in other directory. So now with this, improving our CMake file, if you remember, we had a source directory for our source files, the build directory where we are actually creating all the CMake and make stuff, and inc where our headers were in the project. Now we have a couple of extra directories: bin for the final binary, and lib for the library mylib. So mylib will be written here once generated, and myx will be here. So the make file that will be created once CMake is executed will have these rules to create these binaries in these specific locations. Remember, CMake CMake in the end is just creating a make, and make will be actually building our project. So these are just instructions to create a make to perform these actions. So a typical project organization usually includes multiple sub-projects. For example, here we can consider that the executable and the library are different projects. And well, it depends on the size. This can have sense or not. But it's quite usually to have multiple libraries and multiple binaries that are part of the same project. But usually with different headers, different source files. So usually it's a good idea to have in different directories, because that way we can encapsulate here the different files related with every sub-project. So this is a good organization, and we can also have something like this. How to move from this one, in which all our source files are here, to a hierarchy with different sub-projects? Well, basically we need now multiple CMake files. In this case, we need a parent CMake file that, in this case, I'm putting in the project root, and specific CMake files for every sub-project. The rest is like in the previous slide. So now, as you can see, in the parent CMake, we have the name of the project and the version, and I'm specifying bin and lib as destination for our binaries. And after that, I'm telling CMake that I'm using these subdirectories where CMake can find the corresponding CMake files. So I'm telling CMake here we have relevant stuff, and also here. And then CMake will parse these two CMake files, and each CMake file now has a specific information for that subproject. So here for the executable is just telling the name of the binary, the dependencies, that it needs this library, that is the other subproject to be built, and where are they include the header, sorry, and also maybe it's quite common that the library has some libraries that need that the compiler can find the definitions in some header. So probably the library has its own headers in this directory. So any binary using the library needs to know to previously use the headers in the compilation step. So we need to also include this in most projects with this structure. And finally, how to compile which flags to enable in the compilation step, and the same information for the library. So with these three CMake files, we have a better organization in our project. Okay, some improvements on top of this. So this is the more complex organization I'm proposing here. Of course, we can also improve this. Now I will give some improvements regarding, for example, building different types of executables. Again, like in the example with the make files, usually we want to be able to build a debug version or a release version, or even these are typical possibilities: debug, release, release with deb info. That means release with debug information. The difference between debug and release with debug information usually is that debug is usually compiled with optimizations, but release with deb information is with debug symbols, but also optimizations. Well, this is sometimes also used. It's especially important in, for example, embedded systems. That means to have a release, a binary of minimum size. There are specific optimization flags in compilers. I don't know if I commented this the other day, but in GCC, for example, we have -OS and -OS optimized for size. Optimizes for size. This is especially important above all in embedded systems. Embedded systems are like computers, but with a lot important constraints of memory and, well, a lot of different limitations. And the memory constraint is important, so usually the size of our binaries is relevant. So we can also have this constraint of size, and we can build a minimum size version. To choose between these build types in our CMake file, we can use this variable. So that way, CMake is helping us to create the different versions. So when we are calling CMake, we can use this -d, and with -d in CMake, we can assign a value to one of the internal variables in our CMake list. This works for whatever variable, but in this case, it's relevant to choose the kind of build we want in CMake. So we can choose debug, release, and in our CMake list, we can take that into account, choosing different combinations depending on the build. And here in this example, we are choosing different combinations depending on the compiler, because we can also have information about the compiler in our variables. So if CMake is compiling using GCC or CCC, we can choose different compilation or linking options. This is quite interesting because with makefiles, we have to do this at hand. But here in CMake, we have facilities for this to know the compiler we're using in our CMake and take decisions taking this into account. Finally, the find package I mentioned earlier. Find package is very important because it's the way we can include different libraries and different stuff we didn't write ourselves, but are in the system and possibly in different locations. So depending on in one system, these packages can be in one path, and in others can be in others. So this find package is in charge of looking for this software. So when we're using CMake, the different software install a package like this: OpenMP, MPI, CUDA, and this package has some files. There is a standard for this that allows find package to find where this is installed in the system. So this allows CMake to create a make file with the appropriate paths to find everything in the computer. So for these are two typical examples. OpenMP, we find package OpenMP. If OpenMP is installed in the system, we can have the paths of OpenMP in our make file, and the same for MPI. We have the documentation of CMake that is telling us how this, which variables are these two packages creating, variables that we can also use in our CMake. Okay, finally, with CMake, instead of make, we can use Ninja. So just using -G here, we tell CMake that we want Ninja to generate the project instead of make. So in this case, after executing all the CMake stuff, we use Ninja to generate the final binaries instead of CMake, instead of make, sorry. Okay, so this is basically the idea of CMake. I don't know if you have any doubt. If no, I want you to try to create a simple CMake. Here you have some documentation. Forget about Valgrind because it's in other block. Well, actually, most of this is in other block. Don't pay attention to this. This slide is for other block of slides. And here you have the task for now, for this last part of the session. So the idea is that you clone this repository. Again, this is a new repository. In this case, you have some examples of matrix multiplication. You can try the make file included in the repository. And the idea is that you create a simple CMake file for this repository to generate an out-of-source compilation. Out-of-source, remember, means that you will create a build subdirectory in your project. In this case, the project, I can write the correct project. Let me. So this out-of-source means that in our project, that this is the directory, HPC lab. After cloning the Git, you will create a build subdirectory, and you will perform all the stuff here. From here, you will do CMake ... and this should create the corresponding make file in this directory, build. So in HPC lab, that is the parent directory, you are supposed to create your CMake list txt file. So this is the idea. Please use these compilation flags, ASCII flags, and create this. So I start with this simple step, just to create a very simple CMake example. But after this, I want you to try to create two different subprojects in the same project. So these are two different tasks. The first one is very simple, I think, and the second one, well, is a little more complex. Here you should create two different projects like this scenario here, similar to this, actually very similar to this. One is for a library, another one for an executable that will use that library. Sorry, here. You have the instructions here. So just follow the instructions. And the last step is that you try to generate, so after you execute CMake, you could generate with Make or with Ninja your final project. So try both. You can also have a Ninja in finished array. You need to load the corresponding module. And this is optional. If you want, I have a look at your work, create a commit. Remember, you are working with a local repository, so you can create a local commit, and you can pass me your commit. With this command, format patch, you can export commits in your local repository to text in a way that later you can pass by email. I can give you an example. Imagine here in my previous repository with the previous example with the make files. Imagine I want you to give you this commit, the last commit here. Format patch with -1. I'm telling this git command that I want just the last commit. With 2, with -2, I'm telling I want the 2 last commits. So there are other ways to indicate commits, but this is the simplest one if we want the most recent commits. So imagine the 2 last commits. So now this command is creating these 2 files, these 2 patches. Patch and commit is basically the same in control version jargon. So you have now these 2 patches. We can have a look at the patches. Basically, these are files with differences. So here you can see the commit. In this case, this commit is very simple. I just remove in the make file. I just add. This was the original line. And this was my version in this commit, this change introduced by this commit. So the important thing here, with these 2 files, I can attach these files in a mail or pass you the files by Teams in a chat, and you can apply. I can apply your patches easily, just with git am. With this command, I can apply any patch in my local repositories. It's a good way to share your commits with other people and try the different commits. So that's what I was asking you optionally in the last task here, that you pass me your work just to have a look at it. Okay, so you know what I'm asking you? Well, basically it's just to read this slide and to follow the instructions, but at least try to create the simple CMake and to perform the out of source compilation. And after that, we can think about if continue with the next step or move to other stuff, because we have well, less than an hour now. Okay, so I try it. So I put here the slide. you should be able to follow this link in your viewer and reach the repository. Let me try it. So this should lead you to this repository. And again, you can clone this. HPC lab. Tell me.
How do we have to do we have to do it in Finisterra or in our computer?
You can decide it. You can do it at Finisterra or in your local computer. It's up to you, and it depends on the facilities you have in your local computer. If you have CMake, a compiler, and so on in your local computer, you can do it in your local computer. That is probably, or well, it's easier than in Finisterra. But it depends on your system. So you have a compiler in your computer. You can compile C code.
Yes.
If you can do it, if you can compile C code and you have make and CMake, you can do it in your computer. Try it. Otherwise, you can try to. Well, CMake is just if you are in a Linux distribution like Ubuntu, Debian, or so on, with a package system, you can just install CMake very simple, very easily, like this. For example, this works in Debian-based distributions. apt install CMake, and that's enough. But it depends on your system. I don't know which system are you using. I can do it here because actually in this computer probably there is no CMake. You want the? I can do it here. No. So no CMake here. You can see it. So no. So I'm installing the package. This is an Ubuntu system. And now I have CMake. So this was the line to install CMake. In case you don't have CMake in your local computer, if you are using Debian, Ubuntu, or based distributions. You need help? What's the problem? It's okay, okay. Don't hesitate in asking me or in asking for help. You can interact with each other, of course. This is not an exam, so you can interact with each other if you want. Tell me.
I know when I launched the main command with the trial the git,
Yeah.
good, and when I do just the command
Yeah, because it's same as already yeah, because it depends on the system. You can fix that. Just edit the main file. This is the original main file.
Yes.
Yeah, just edit the makefile.
I can edit.
Yeah, you can. And then the stuff. You need to add you can add and delete. I think my username is enough. Let me check the rules. For example, the drawing here that we are creating a lot of at least one, it's fine. Okay, we already know about here, for example. Explicit project, explicit motion. Now we need to add the variable. Yeah. Right now. Yeah, the problem is that it works. Yeah, okay. I don't know what. Okay.
Thank you.
You're welcome.
Emilio,
También.
instalando, bueno, haciendo el make, después del CMake, no me compilan local creo que por las instrucciones AVX. ¿Puede ser que haya algún problema con máquinas
Claro,
virtuales?
claro. Sí, claro. Tienes toda la razón. Claro, no me di cuenta. Ese código tiene una vectorización. Claro. Déjame que le eche un vistazo. Es que he cogido el código que tenía del año pasado y es posible que en local tengáis problemas. Déjame echarle un vistazo.
Sí, lo digo, si hay alguna manera fácil de solucionar la dependencia, guay. Si no, hay que compilarlo en el Finisterrae, ¿no?
Claro, es que no lo había pensado. Déjame ver que le eche un vistazo yo a esto. Claro. En este ejemplo, que además quería usar luego para enseñaros, bueno, no sé si hoy me dará tiempo, quería volver un poco al tema de las vectorizaciones. Y aquí tengo una vectorización que hice yo directamente, para que veáis precisamente que no es una cosa especialmente agradable de hacer. Mejor si lo puede hacer el compilador por nosotros. Vale, entonces déjame ver lo que estoy haciendo aquí. Claro. Exactamente cuál es el error que te dio.
Mira, te paso una captura.
Sí, pásame una captura. Porque, si, por ejemplo, el makefile, antes de usar CMake, el makefile te funcionaba, ¿no?
Sí, sin ningún problema.
Vale,
al momento de hacer el make.
Vale, pero el make del CMake, ¿no?
Sí, correcto, el generado por el
Es
CMake.
decir, el make que venía por defecto en el proyecto te funcionaba.
Ah, no lo he probado. No,
Vale, pruébalo, porque si ese te funciona, entonces
no, tampoco.
Claro, tampoco, te da el mismo error.
Sí, si no es el mismo, sí, es el mismo.
Vale, déjame verlo, a ver. Porque a mí, por ejemplo, en este equipo en el que estoy, que tampoco es un equipo, vamos, no tiene de particular, sí me está funcionando.
Puede ser porque estoy en una máquina virtual.
Podría ser, déjame ver. ¿Tienes el comienzo del error? Claro, veo el problema.
Sí,
Esas instrucciones de las que se está quejando son lo que se llaman intrinsics, que comenté el otro día de pasada, cuando empecé a hablar de vectorización, y sobre esto quería volver hoy. Para usar a pelo las instrucciones vectoriales en un lenguaje de alto nivel, como puede ser C, claro, las instrucciones vectoriales son instrucciones máquina o ensamblador, es decir, tendríamos que usarlas en ensamblador. Para no tener que andar mezclando ensamblador con C, que se podría hacer, pero para no tener que hacerlo, lo que proporciona Intel son una cosa que le llama intrinsics, que vienen siendo una especie de pseudofunciones que te permiten acceder a estas instrucciones en ensamblador. No sé si estoy hablando de algo que te resulta muy ajeno o lo estás entendiendo.
Entiendo lo que dices, pero nunca he trabajado a tan bajo nivel.
Vale,
Pero
vale.
entiendo lo que me estás diciendo. Sí.
Claro, digamos que tenemos unas instrucciones en esos procesadores, que son las instrucciones AVX, que son instrucciones vectoriales, que el compilador puede generar código para ellas, pero nosotros también podríamos, como programadores, explotarlas. Y para no tener que hacerlo en ensamblador, pues tenemos estas intrinsics, que son funciones que la verdad es que tampoco es que varía mucho a nivel de complejidad, pero bueno, no tenemos que andar haciendo para embeber un ensamblador en el código C, pues siempre hay que hacer alguna historia y esto es más simple. Podemos meterlo directamente en código C, esas intrinsics. Pues parece que no las está encontrando o algún problema le está dando en este error que me pasa. ¿Saben en la otra captura?
Es muy similar. Es simplemente que el stack es bastante largo, pero
Sí.
todos los errores, pero es lo mismo.
No sé de qué se queja. ¿No te crees que lo tengo muy claro? Este es de lo que se queja el CMake, sí. O sea, el otro dices que hace lo mismo.
Este es el del CMake, el del make
Sí.
te lo puedo pasar. Pero
Sí, pues supongo que pondrá lo mismo, pero como este CMake no está verbose, cuando ejecutamos CMake, podemos pasarle la opción verbose igual a 1, creo que es así, hablo de memoria. Podemos hacer CMake. Perdón, cuando hacemos el make del CMake, podemos hacer esto. Y no nos oculta cosas. Así podemos ver las líneas de compilación exactas, porque así solamente veo los resultados de compilación, pero no veo la línea exacta que está usando CMake.
Sí, ¿cómo es la línea? Que lo
Les
lanzo ahora.
Se pone
Estaba mirando.
igual a 1.
Vale.
Bueno, es bastante verbose, ¿eh? O sea, crea bastantes líneas, pero realmente si quieres, cuando te da un error de compilación, si quieres saber exactamente cómo está invocando el compilador, pues necesitas verlo.
No saca mucho más. Espera, creo que le puedo pasar un fichero. O si quieres te comparto pantalla, como prefieras.
No, pero como en el make ya veo la invocación.
Es que no me saca mucho más con el verbose.
No te preocupes, así es suficiente con lo que estoy viendo ahora. Pues no tengo muy claro cuál puede ser el problema, la verdad.
Haciendo bueno, mirando en Stack Overflow, haciendo un grep de AVX y AVX2 en proc CPU info, en principio aparece.
No, por ejemplo, de una cosa que vimos el otro día, para saber si tu procesador tiene de eso, por ejemplo, si tú haces GCC menos Q, help igual a platform, creo que es menos help. Y ahora, o incluso mejor, ponemos menos Q, menos march, menos march, igual a native. Espera, que algo estoy poniendo mal. A ver, que estas cosas de memoria nunca me las sé. Déjame que lo mire en la diapositiva. Aunque lo he hecho 1000 veces, que yo creo que es así, pero algo estoy haciendo mal. Bueno, voy a mirar. Que me centre. Aquí tenemos. Vale. Vale. Menos Q. Ah, vale, que me faltaba esto. Vale. Vale. Vale, con esto deberías poder ver las opciones que realmente la familia de procesador que estás utilizando y GCC detecta cuál es la arquitectura, digamos, de tu procesador. Entonces te pone aquí el march concreto y ya ves precisamente si te dice que AVX y demás está activado o no.
Menos march me pilla Skylake.
Eso es bastante nuevo. Y debajo estará enable, tanto AVX como AVX2.
Sí, no, espera. Sí, enable ambos, sí, correcto.
Sí, o sea, el problema no es
Sí.
ese. Entonces, no sé por qué te está dando problemas al compilar, la verdad. Tengo que mirarlo. Vamos a ver.
Voy a probar lo mismo en el Finisterrae. A ver, voy a hacer un SCP.
No, da la impresión de que te falta algún header. Pero no estoy seguro, es que no parece eso. Dice mismatch, pero no sé muy bien a qué se refiere. Que funcione, ya te digo que a mí me está funcionando en este ordenador salchichero que tenemos aquí. La otra opción, si quieres hacer en local, pues no utilices esa la implementación vectorial, que es la que está con matmul kernels AVX. Esa no la incluyes y ya está en tu proyecto CMake y ya está.
Vale. Bueno, yo era un poco por...
Claro.
Aunque trabajemos en el Finisterrae, siempre me gusta probar las cosas también, tener la opción de probarlas en local.
Sí.
Era así, igual, no sé, igual me sale este problema más adelante otra vez o algo.
No, voy a buscar, a ver si se me ocurre cómo solucionarlo. Yo también prefiero probar las cosas en local que andar con el lío del Finisterrae. Otra cosa es luego para obtener el rendimiento y tal, pero para probar. Curioso. Yes. It seems there is something is blocking your access to maybe you have any other. Can you have a look? Can you write the heroes in what the wrong is? The same person instead of DPKG, to write the APT. No, sure, more sorry. I'm going to add more. I'm not sure what you're doing. Why the touch? But usually in Unix or Linux, you use touch to modify the date of the file, to update the date. But I don't know why you don't do that. What's the purpose of your touch? Your touch file. Yeah, with touch you also create a file if it's not. Yeah, that's a side effect of the real purpose of touch. Yeah. So you create a file if it's not. Okay, yeah. So you're using touch to create a file. Yeah, but it's an empty file. So you need to write the different lines in the slide. At least the simple version. You have to decide. Yeah, the simple CMake list in the first. Yeah. With the right target. Because otherwise, if we apply a self-estimate, a ver, perdona, estoy de vuelta. Aún no he podido mirar eso, David. Un momento. Yo también he encontrado en Stack Overflow alguna referencia a eso y la gente, en principio, parece que lo intenta arreglar añadiendo algún flag más del compilador relacionado a las instrucciones AVX, pero me parece extraño porque cuando le pones march menos native, pues ya le estás diciendo que utilice AVX, teóricamente.
Ya, es un poco raro. Bueno, funciona perfectamente en el Finisterrae. Entonces,
Prueba añadir esa línea en el makefile, que es más rápido quizás que andar con el CMake. Prueba añadirle en la línea, además de donde pone menos march native, prueba añadir menos AVX2 o menos cosas así, pero ya te digo que no me parece que tenga sentido. Digamos, es que está implícito.
Sí, no, probamos a ver qué tal.
Tiene que ser otra cosa.
No. Ah, vale. Que va con AVX2. Bueno, voy a buscarlo un poco en internet a ver qué encuentro. Creo que ya encontré el problema.
Ah, sí,
Es
pues
decir, me parece que hay que habilitar la virtualización dentro de la máquina virtual. Es un tema de...
Ah, vale, es un problema de paravirtualización.
Sí, es los míticos 2 ticks que hay que marcar para poder virtualizar dentro de una máquina virtual. Bueno, lo pruebo ahora y te digo.
Vale, entonces eso
tiene toda la pinta.
Vale. Okay, since it's 10 minutes to finish the session, we are not going to have a look at the vectorization stuff I was thinking about for the last part of this session. So in the next session, we will start with that, with some details from the last session, from the previous session regarding vectorization, and we'll use also this repository you are using now to create the CMake. Okay, David is pasting the solution. Okay, with that it's working.
Sí, funciona así.
Okay.
No era el tema, no sé cuál era el tema. La virtualización la tenía activada en la máquina virtual, así compila. No sé, tendría que leer la documentación a ver por qué.
Es curioso, sí, es curioso porque, ya te digo, en ninguna de mis máquinas que tengo aquí el portátil, estoy con este escritorio donde estamos dando la clase, en ninguna me hace falta poner nada, claro. Más allá de March Native. Teóricamente, cuando pones March Native, además acabamos de comprobarlo aquí en este equipo, si tienes una arquitectura relativamente moderna, pues ya te incluye el AVX2 by default. Es decir, yo creo que
yo me tengo encontrado trabajando con temas de instrucciones y tal, con problemas de estos, trabajando con máquinas virtuales, me he encontrado con un montón de problemas. De que debería funcionar y no funciona, que todo entonces vale, no,
si funciona,
casi da igual. Si funciona
vale,
así,
si funciona perfecto. Vale. Vale. So I was telling you that we will finish today's session with this. So just work this 5 minutes until leaving. Try to compose a good CMake. Ask me any question, and after leaving, if you want that I review your work, you can finish it at home if you want. This is an optional. Today's tasks are not. I'm not evaluating this task, so you can. If you want to review your work, you can pass me your work any of these days, and I can have a look and tell me my feedback. So if you want to do it, try what I was telling you. 1 minute, Priscilla. Yeah, try this approach to create your own commit and pass me the patches if you are comfortable using Git. So this is a good approach to give me your CMake. But if you are not comfortable with Git and you prefer just pass me the CMake files. But well, for the third task, that is involving the whole structure of the directory, the whole hierarchy of the project, is to be able to understand your CMake, and if you have any issue, what's happening. I need the whole stuff, the different subdirectories, the different CMakes. So that's why it's a good idea that you pass me your work as a Git patch. Otherwise, you can just zip or use any other compress tool, and give me attach that in an email or by Teams. And that
can we invite you to our GitHub repo?
Yeah, and you can also do you can create your own branch and ask me for a pull request, and I can incorporate your branch in the remote. But well, you can use whatever approach you prefer. Invite me to your own repository is also okay. Tell me, please.
I want to ask for the first step, the last professor asked us to add to give, but if it's you correct the text, we have to add you again as
Yeah, you can add both of us. So the one you mean. Yeah, for the first task. Yeah.
For the task, okay.
Yeah, I think it's already. I don't know who is the. I don't know. Yeah, well, me will split the correction. We have 3 tasks during the course, so I don't know how we will split that. But it's already that you have the both of us in both in your task in the evaluation.
Okay.
So this is not the case for this because this is just an optional part. This is just if you want to practice with this and you're not sure about if it's okay or if you are interested in that I review your work, just let me know.
And you see my
I'm not sure. Yeah, maybe it was. Yeah, let me. I think it was an email or yeah. I had these days. I have classes in the morning and in the afternoon, so my email is a little bit growing these days. So let me check. What's your name? Let me. I have a lot of emails without answer. Adrian. Okay. So yeah, I have your email. Thank you. I will answer when I have time for reading it.
I have just a question.
Yeah. Please.
It's on the mail.
Okay. So this is your mail. Yeah.
Okay, I was not really sure
Sorry.
for this column.
What do you mean you're not really sure? You're not sure if
The
you.
option that I had to type for
The idea that was that. Yeah. The idea was that. Sorry. Something like this. So in the make, the idea was using both fast. This was the idea.
That's what I did, but for the last column.
Sorry for that. Yeah, without the margin native for this one and with the margin native for this one. So that's the difference theoretically. So
If it takes longer, I don't get but just
maybe it's okay.
It's okay, yes.
No, maybe it's okay if you. Yeah.
Because it's a really okay. I get it.
Okay, you're welcome. I have to see my times, my ideas to compare your times with mine, just to be sure everything has sense. Thank you. Okay, so you can leave whenever you want. See you on Tuesday, and let me know by email or by a Teams message if you need any help or any review of your CMake or your make. Because my idea with this is that you really understand how to use these tools in your own projects. For example, in your task, you could use this also.
At the end, you say we can commit our code.
Yeah. There are multiple alternatives for this. So you, for example, can do something like this. Imagine here. Imagine here I introduce whatever change. Just here an important change. So this is a change. So now with this change you can, for example, create you have this change. You can create a new branch, or with my name, for example. Sorry. With something like this, you create a new branch. Now I'm in the new branch, and in this branch, I still have this change that I didn't commit yet. I haven't committed yet, so now I can commit this. Ciao.
It's a public.
No, this is local. All these commits are in your local machine. Right now, I'm doing this in local, so you can create all the commits you need. It's in your machine. Now, how to share this work with me? That's the question. You have multiple alternatives. For example, you can apply this alternative here. Sorry. Git format patch. With Git imagine you create even multiple commits, other commits. I don't know. Then just inventing. Bye bye. So a new commit. So I have two new commits in this branch, and imagine I want to share my commits with you. These commits right now are in my local machine with this two with this command -2 because I want two commits in files. Now I have these two files in the same directory. Each of these files are each of these two commits. So you can attach these files in a mail,
Okay.
or you can pass me these files by any means, these two files, and I can apply these files in my local repository, and now I have your commits in my repository.
Okay.
So that way I can have a look. But if you prefer, you can create your own remote repository, upload there your changes, and share. Give me access. I don't know. It's up to you to choose. If you have doubts or you are not sure how to do this, just let me know by email or by Teams. I can help you to do it.
It's a new one. I didn't know patch.
Yeah, I understand that you've never did this, so you've never done this, so it's I understand the difficulty. Yeah, so that's why I just write here the name of the command. So have a look. If you have problems, just let me know. It's in the end, it's very easy.
Okay, I will try it. I think.
Okay. Okay. Thank you. Okay. So see you on Tuesday,
Yes.
everyone. Bye bye.
Bye.